Welcome everyone to Étale cohomology on November 10th, 2020. So last time we began the discussion of Poincaré duality, and I sketched the construction if X is a smooth variety over a field K of dimension D. Sorry, here K is separably closed. Then I sketched a construction between H2D compact support X and then lambda of D. I'll say in a second what lambda is. So I construct a trace map between this thing and just lambda, where here lambda is the sheaf, the constant sheaf Z mod L to the NZ, or ZL, or QL. Here we're thinking of these as, these aren't sheaves, these are ZL sheaves or QL sheaves, meaning a ZL sheaf, remember, is an inverse system of sheaves. So we constructed an isomorphism like this. So this was an isomorphism. And so today I'm going to use this. I'm going to sketch how we're going to use this to construct kind of Poincaré duality. And then I'm going to sketch the proof of the Lefschetz fixed point formula. And that will be a conclusion, actually, of all the preliminaries we need to start getting at the Weil conjectures. So assuming I finish these today, we're going to start proving the Weil conjectures next time, or even maybe at the end of today. So in particular, with this and the finiteness theorems we've already proven, doing the rationality and functional equation, like in the first couple lectures of the course, will be not very hard. And then the Riemann hypothesis will take a lot of time. All right, so are there any questions about that before we continue? Okay, so what's let me first recall the statement of Poincaré duality. So at least the simplest statement was that there was a cup product map from HI compact support X lambda of D times H2D minus I of X without compact support lambda to H2D. So this is a cup product map. Compact support of X with coefficients in lambda of D. And we just said that this is canonically isomorphic via this trace map to lambda. And the statement was that so this makes sense in general, and the statement was that if lambda is QL, this is an isomorphism. This is a perfect pairing. So in general, the obstruction to being a perfect pairing is some torsion stuff. There's still some torsion version of Poincaré duality, which I'll say a word about. But this is what we'll actually use when we prove the Weil conjectures, which are just about, the Weil conjectures are just about rational cohomology, since they're about the traces of some operators acting on cohomology. So this is all we're going to care about later on, but I'll say a word about the torsion situation, since Ben asked about it a bit in office hours. Okay, so what's the idea? So I'm only going to sketch the idea because this is a very involved proof. So the idea is actually to find a relative version of this. So to find a relative version which is called Verdier duality. So just a reminder, so there's some categories I've only very imprecisely described, which are the derived categories of constructible sheaves on X. So suppose we have a morphism f from x to y. This is just a morphism of k varieties. And this works in more generality than k varieties, but we're only going to use it for varieties. So then there's a map r f lower shriek from the derived category of constructible sheaves. I'll say what this means in a second, on x to the derived category of constructible sheaves on y. So just a reminder, I sort of briefly discussed this. So this is you take the category of complexes of abelian sheaves, so category of bounded complexes of abelian sheaves on the Étale site, and formally invert quasi-isomorphisms. And these complexes have to satisfy an additional property. They have to have constructible cohomology. Okay, so loosely speaking, what you should think of these complexes as is they're complexes of abelian sheaves, which are built out of constructible sheaves. So in particular, their cohomology sheaves are constructible, and then we're only viewing them up to quasi-isomorphism. So if you haven't seen the derived category, this is a very sketchy introduction. If you've seen the derived category of an abelian category, that's what this is. So you take the category of bounded complexes of abelian sheaves with constructible cohomology sheaves, and then formally invert quasi-isomorphisms. So what's the benefit of this? So the benefit of this category is that it lets one study the sort of total derived functors. So here this is a functor which takes a sheaf on X, for example, or a complex of sheaves, and then sends it to a complex computing as the cohomology sheaves, the derived Schriek push forwards of the complex you started with on X. So for example, if you started with an honest sheaf here, what would this functor be? Well, you'd extend your sheaf by 0 to a relative compactification of X. You'd take injective resolution of it, and then you'd take the push forward of that injective resolution, and that's all it would be. So what this says is like, oh, well, that operation, which involves a choice, namely the choice of injective resolution, actually gives you a well-defined functor once you invert the sort of things your choice is up to, namely quasi-isomorphisms. So are there any questions about what I mean by this map here? I'm happy to talk more about it, and I know that was a very fast introduction to it. So if you have questions, now's your chance.
Why do you take complexes of sheaves with constructible cohomology and not complexes of constructible sheaves?
That's a good question. So as far as I know, it's at least not obvious to me that those two categories are equivalent. The reason this is a convenient thing to do is when you compute these derived functors, like RF lower star, say, you take an injective resolution, right? And those injective sheaves that you use are not constructible.
I see. So you want to have like enough acyclics in
Yeah,
your
that's
category.
right. That's right. Yeah, so there are a lot of situations. I mean, so the actual construction or definition of the derived category doesn't require that. So usually what it does is it lets you actually define these functors. There are actually a lot of situations, and I think this is not one of them in general, but there are a lot of situations where you can kind of use the smaller category and you end up getting an equivalent derived category. But it's like, for example, if you have a scheme, you can look at the derived category of complexes of coherent sheaves, or you can look at the derived category of abelian sheaves with coherent cohomology. And those are not always equivalent, but in good cases, like for varieties over a field, they are equivalent. But in sort of general situations, the sort of safe thing to do is always to take a category of complexes in a sort of very like floppy situation, like all abelian sheaves, and just put restrictions on their cohomology.
Okay.
Yeah.
Thanks.
Are there any other questions about this? Okay, so the idea now will be to construct a right adjoint to our F lower shriek. So this is something that in general only exists on the level of derived categories. So this will be a what we'll call F upper shriek, and this will be a map from the category. Well, this is called constructible derived categories. That's what I'll just refer to it as. So the constructible derived category on Y to the constructible derived category on X. So this is step one. One will construct a sort of right adjoint in general, and then step two is to actually compute it. So compute that if F is smooth of pure dimension D, then this F upper shriek functor applied to a sheaf or a complex F will be F twisted by D, and then in degree 2D. Okay, and then 3. So this adjointness is going to imply, this is more or less an unwinding of what adjointness is going to mean, that if one computes R F lower star of the derived Hom functor of F into F upper shriek of G. Sorry, this is really crazy, but I'm going to work out an example in a second. This is going to be, there will be a canonical equivalence of bifunctors, if you'd like, into R Hom. So here this is in dc of X, and this is in dc of Y, of R F lower shriek of F with coefficient mapping to G. Okay, so this is some crazy stuff. Let me briefly indicate why this implies Poincaré duality. So what does this have to do? With Poincaré duality? Okay, so the idea is very simple. So the idea is you take X to be any smooth variety, Y to be a point, and F and G to be sheaves lambda to be a constant sheaf. So you think lambda is QL, but I want to write it in. So this is a constant sheaf. So you should think lambda is QL, but I want to write it in this generality because it will let me make some remarks about like what happens with torsion and that kind of thing. So what happens? So then we get an if you believe this adjointness, so we get an isomorphism R F lower star R Hom. So R Hom just means the derived functor of Hom, so it's cohomology sheaves or X sheaves. So now we get lambda, then F upper shriek of lambda here. So what was F upper shriek of lambda? In this smooth setting, this was just lambda twisted by D in degree minus 2D. So this shift here means we put it in degree minus 2D. And then this was supposed to be isomorphic to R Hom. This is now on the point, so I can erase the underline. It's just R Hom of lambda, sorry, of R F lower shriek of lambda into lambda. Okay, so what happens? So what is this top thing? So this top thing is pretty understandable. This is just the so this R Hom here. So let me highlight it maybe. This R Hom here. So this is just R Hom from the constant thing into a twist of the constant thing is just a twist of the constant thing in some degree. So this is R F lower star of what is it, lambda of D twisted by in degree minus 2D. So in other words, this computes the cohomology. So H 2D minus I, if you'd like. Sorry, this computes wait, sorry, let me just quickly check which direction it is. Yeah, so in negative degree. So in degree, the cohomology of this in degree I is H negative 2D plus I of X with coefficients in, wait, sorry. This is in negative degrees. Sorry, it computes HI plus 2D of X with coefficients in lambda of D. So this is cohomology in negative degrees. So its cohomology runs from H minus 2D to H0. So what about this thing? So the cohomology here, well, there's a spectral sequence computing this, which goes from X to I of, well, our F lower shriek of lambda is just the compactly supported cohomology of X with coefficients in lambda, but then we're mapping that into lambda. Okay, so if lambda is just QL, so what happens? So if lambda is just QL, then this X term vanishes, and what we get is a isomorphism between the dual of Hj X lambda with compact support and H, let's see, J minus 2D of X lambda of D. And I think I'm probably missing a minus sign here because of the dual. So I think this is a minus J. Yeah, that's right. So, so this is just Poincaré duality. Now, of course, there's a bit of content here. So first of all, you have to unwind the pairing here. With this isomorphism gives one a pairing between this and this, right? And one has to compare that to the cup product. That's a highly non-trivial thing to do. And then one has to check compatibility under that comparison with the trace map. All right, so let me just briefly remark. So what happens for like lambda is ZL? So for lambda ZL, you get a special sequence. So X I of H with compact support J, X lambda, and this converges to the thing on the right, which was H, I think we get I minus J plus 2D of X lambda of D. So what's happening here? So some of these pieces are torsion. So when this group has some torsion, then X1 is non-zero. And if lambda is Z mod L to the N, things can get a lot more complicated. So in that case, these groups can be non-zero for infinitely many I. All right. Are there any questions about that? So this is kind of a general procedure for studying like versions of Poincaré duality. So for example, there's a version of Verdier duality in topology. So for nice maps of spaces, like not just manifolds, there's a version of this F upper shriek functor, and it lets one kind of have a version of Poincaré duality on pretty general topological spaces. So this is a really, I mean, it's a very beautiful theory, and I encourage you to look at it. So the place where it's computable is this in the smooth setting. So in topology for manifolds, when this F upper shriek has a nice form. Okay, so let me say a few words about these constructions because they're not at all trivial, and I mean there's like books written about this. It's not you know, I could teach a whole course on this. But what have we bought ourselves? So what we've bought ourselves is we've bought ourselves some room to actually construct this F upper shriek. So in particular, suppose we can write F as like a composition of two maps, so like H and G. then if we can construct H upper shriek and G upper shriek, then we can construct F upper shriek as their composition, as the composition. So what this lets us do is it lets us reduce things to the case of relative curves, which is basically the benefit. So what's the let me just say so that's actually the original construction, but let me just say a bit about the modern construction of F upper shriek. So this is due to Niemann. So this is for general F. So the idea is to use Brown representability. So what that is it's a general criterion for when a functor on a sort of homotopy theoretic category. So for example, like in a model theoretic setting or in a triangulated setting is representable. And what you do is you just figure out, so what do you want to do? You want to figure out, so what is the functor? So what is the functor into F upper shriek of G? And well, we know what it is. It's equal to of F star dash into G, more or less. Like this is what it means to be adjoint. So this should be, sorry, R F star into G. So this is what it means to be adjoint. So what one needs to do is one just needs to check that this functor satisfies the conditions of the Brown representability theorem. So one checks that this is representable, and there's an abstract way to do that. And now one just has to compute what it is. So now one has to compute it for F smooth. And the idea is to reduce to the following situation. So one reduces to the case where F from X to S is smooth of relative dimension 1. Your sheaf F here is constant, so that you can do by taking a resolution. Well, and some other depassage. So G you take to be constructible. Okay, and then this is in some sense a direct computation. It's still a highly non-trivial computation. Like it's very closely related to what we already did for curves. But one simple trick is that at least if S is a point, we can actually reduce to the situation over C. So why is that? Well, we've already proven a bunch of comparison theorems between Étale cohomology in this kind of setting on and the analytic situation. And if you have a curve over a point, you can always like lift to characteristic 0 and then pass to the complex numbers. So in some sense, these computations are like, you don't have to use analytic methods, but at least some of it can be simplified if you do. Cool. Okay, so once you compute for a relative curve, then at least locally you can write any map as a composition of relative curves, or any smooth map as a composition of relative curves, and then you win. There's some non-trivial details in actually, like this is not quite a local statement because it's in the derived category, but at least for smooth morphisms, since everything is like this F upper shriek is actually an honest. You can write it as an honest functor, not just on the derived category. Like we said F upper shriek of F is just F of D. Well, then there's this shift, but let me ignore that for a second. Like this is at least this part. Sorry, there should be an F upper star here. At least this part makes sense. Not in the derived category. Like somehow the gluing implicit in checking this locally is not actually very challenging. All right, are there any questions about that? That was a very, very sketchy intro to Poincaré duality. So you should ask lots of questions.
Well, lambda isn't actually a sheaf, right? It's like an inverse system of sheaves.
That's right, yeah.
So when we're taking x of it, what does that exactly mean?
Yeah, so the way I wrote here, when I wrote this, I wrote it in the derived category of honest constructible sheaves so that this all makes sense when lambda is just C mod L to the NZ. And then making the derived category of L-adic sheaves is really challenging.
Right, but you said something like x, vanishes and above
I
x1.
see what you're saying.
Right?
Yeah.
So like that's not going to.
Sorry, that was in the case where we have this is over a point here, so then there's no actual issue.
Okay.
Right. This x is in the derived category of a point, which is just the same as the category of ZL modules. Yeah. So you're right that strictly speaking, this is not. If you think of it as sheaves on the point, it's not a category. It's not a category of sheaves. But if you it's the derived category of a category, which is equivalent to the category of like continuous ZL modules.
So you're saying that the cohomology of ZL on a point is just like the same thing as taking, is the direct limit, but you can just put the direct limit inside.
That's right. That's right. Yeah, I mean, it's not the, sorry, maybe I should be a little clearer. So this is not the category, when you compute this X, it's not in the category of discrete ZL modules. It's in the category of topological ZL modules. So there's still a little bit of subtlety, but yeah, what the statement is that the category of ZL sheaves on the point is equivalent to the category of topological ZL modules. So if you believe you can take X of topological ZL modules, then you should just think in that category. But I actually do think that's subtle. Like it's not a totally trivial thing to do. But yeah, that's a good question.
Well, how do you take X of topological ZL modules?
Yeah, that's a good question. Yeah, so one thing you can do is, so what's the simplest thing to say? I mean, yeah, I guess what I would say is the simplest thing to say is that you can just define things in terms of free resolutions, which is not so hard for ZL modules. If you want like a really good theory, I don't think you can avoid at least some of the pain involved in making derived categories of L-adic sheaves. So what you do there is you take a kind of, you work with the derived category of Z mod L to the NZ modules and then take a kind of inverse limit, but it's a little subtle what that actually means.
I guess I'm not entirely sure. Wait, so topological ZL modules, do those even form an abelian category?
Let me think about that. I think at least for finitely generated ones, they do. I would have to think a little bit in general. It's a good question. Yeah, they certainly form an exact category, which is all you need, but it's okay. Yeah. So Jose asks if step one is to prove the relative trace map is an isomorphism. So I kind of sketched that last time. So here I was explaining how to continue. So step one was just to construct this right adjoint functor. Does that answer your question, Jose? Great. Other questions? Yeah, so I'm sorry I'm going through so quickly through this. Like I think this is not this is quite hard stuff. All right, so let me mention a couple corollaries here. So the first corollary is that that if X is a smooth variety of dimension D, hi of X equals 0, or really we can put anything here. Here, this is any constructible thing. For I bigger than 2D. Can anyone prove the corollary for me?
dual to something in negative degree.
Yeah, exactly right. So it's dual to something in negative degree. We could have, I mean, this is, I think, traditionally proven, I mean, this is true for non-smooth varieties in general, also in negative degree. But this gives a cheap proof. So the remark is that this is actually true for arbitrary varieties. Of dimension D. But the proof is very non-trivial. So it relies on some really like non-trivial Galois cohomology computations. So the idea you want to do is you want to try to fiber in curves and then argue that we know that what the cohomological dimension of curves is, but there's some subtleties that mean working in that relative situation is a little harder. Yeah, so but this at least gives us a cheap proof for smooth varieties.
Do we need the field to be algebraically closed?
Yeah. Sorry, this is smooth variety. Yeah, I mean that was the setting for that we needed that for Poincaré duality too. But yeah, so this is over a separately closed field. Yeah, so the setting is we're over a separately closed field, and then lambda is or f here has the coefficients are prime to the characteristic. Yeah, the orders of the stocks are prime to the characteristic. Yeah, so maybe let me just give you kind of a sort of non-example. So the non-example is that if you have for a curve over a finite field, H3, so let's call it X. So H3, let's say compact support of X, lambda is in general non-zero. Or is non-zero, like maybe, I guess if I put a 1 here, this is always true. Yeah. So this is some kind of, in general for finite fields, there's some kind of Poincaré duality in dimension 2D plus 1. So that's where this is coming from. Cool. So are there any questions about that? Or about anything we've talked about so far?
Where did you use algebraically closed in the proof?
Yeah, so it was in the construction of the trace map. So we
I see, okay.
Yeah, at some point we reduced to the case of curves, and then we used our computation for curves over algebraically closed field. Yeah. Any other questions? Yeah, and I mean, of course, like I think it's not so hard to see you need some condition on algebraic closeness. Like if X is a point, then you know, like field Galois cohomology in general doesn't satisfy Poincaré duality. Although sometimes Galois cohomology has kind of duality features.
Wait, sorry, actually, in your proof using Verdier duality, we didn't really use the trace map. Can we just see where in there we need the
Yeah,
algebraic closed?
so let's see what happened here. So here, yeah.
Is it when we go to the point? Because we need that point to be a...
Yeah, that's right. So what do we see? Yeah, so when here where we used algebraic close it, I mean somehow the trace map is included in this if you like if you take lambda to be lambda of D, and stare at what you get here, you'll see that the trace map just pops out. But what we needed is that sheaves on the point are just honest modules, not Galois modules. So that's where we used it.
I'm just trying to see what fails if they're Galois modules.
Yeah, I mean, so you still get a statement like this, but this X die is in the category of Galois modules.
I see, okay.
Yeah.
Right, so you're saying that doesn't reduce to just the dual when it's...
Right. So what you, for example, in just X0 would be Hom of Galois modules. So it would only pick up kind of the Galois co-invariance in here.
Okay, thanks.
Yeah. Any other questions? These are great questions, by the way. All right, so if not, I want to let's maybe take a 3-minute break actually, because I'm about to start talking about the Lefschetz fixed point formula. So this is a good stopping point. So yeah, so how's everyone doing? All right, no comment. Do you guys actually want a break? Good to hear, Freddie. All right, let's talk a bit about the Lefschetz fixed point formula then. So what's the setting? So suppose X is smooth and projective. We don't actually need a projective, but I'll state things in this setting for now. Over a separably closed field. And suppose phi is a map from X to X. Then the theorem, and I'll discuss what this means in a little second, is that if we take the graph of phi and intersect it with the diagonal, so here this is the diagonal inside of X cross X, and this graph of phi is also inside of X cross X. So this is if you'd like an intersection product in the Chow ring, but I'll say a sort of another way of making sense of it that we already know. So this is the sum of from I equals 0 to 2D of -1 to the I trace of phi star acting on the Étale cohomology of X. Great. Okay, so what does this mean? So here there's two ways of understanding this. So here gamma phi dot delta. So this is an intersection of two cycles of codimension equal to dmx in X times X. So which means its intersection is a cycle class of codimension 2 dmx, so namely a 0 cycle. So this mean when I write this, I mean so maybe I should write the degree here of this. So the degree of this is a number. So we haven't discussed Chow theoretic intersections in this course. So there's another way of getting at these, which is in fact what we'll use in the proof. So in this class, we can think of this as the trace of the class, the cycle class of gamma phi, cupped with the cycle class of delta. So this here is in let's see, 4 dmx. It's the top cohomology of X times X of X times X with coefficients in QL of 2 dmx. And then there's a trace map from this to QL. Okay, and then the non-obvious thing is that these two things agree. So that follows from, for example, the cycle class map being a homomorphism of rings, which I'm not able to prove in this class, unfortunately. But at least from the point of view of proving this theorem, we can just think of it this way. So are there any questions about this statement? So yeah, so what is the simplest way to understand this is in the situation where phi is kind of yeah. So let me maybe draw a picture actually. So here's X cross X. Here's the diagonal. So this is the diagonal. Then the graph of a map looks something like this. So what are these intersection points? These are the fixed points. So in the situation where there are finitely many fixed points, then we can just compute this intersection like literally by intersecting with and counting multiplicities of intersections. And then this says literally, so what you're supposed to think is that this is kind of the number of fixed points. So in general, like if you have a random map phi, like the identity map, for example, this intersection doesn't have to have the right dimension. So for example, one corollary. So one corollary of this is that if you take the diagonal dotted with itself, so the degree of this intersection, this is something that makes sense in the showering or in cohomology, for example, this is equal to the Euler characteristic of the cohomology of X with coefficients. Right, because in that case, you get this, the diagonal is the graph of the identity map. So then you get the trace of the identity, which is just the dimension of these groups. So we're going to apply this later on. So maybe the.
Can I just interrupt for a moment?
What?
Can you specify what maybe I missed the hypotheses. What is X here? Like what is the ground field? For
it's a smooth projective variety over a separately closed field, and I should say L is not equal to the characteristic of K.
So we're allowing characteristic 0 here?
Yeah, for sure. Yeah, so the remark is that even though we're allowing characteristic 0 here, the remark is that this will apply this when phi is the Frobenius map. It's relative Frobenius. Or really, well, actually really absolute Frobenius. All right, so then the fixed points of Frobenius will be literally the rational points of a variety over a finite field. Are there any questions about this? Okay, so in order to describe this, I need to tell you a little bit about Geissen maps. So in order to sketch the proof of this. So let me remind you a little bit about the functoriality. So given a map pi from y to x, which is proper, and suppose we have a proper map and x and y are smooth varieties, we'll later apply this to phi, so where phi is a map from x to itself. So in this setting, we're going to get a sort of dual map, right? So maybe let me assume for a second that x and y are also proper. So then we get a push forward map on cohomology, namely a push forward map from HR of y with coefficients in lambda to h r minus 2c of x with coefficients in lambda twisted by minus c. So this is here where c is the relative dimension of f, or sorry, of pi rather. So by that I mean c is the dimension of I guess dimension of y minus the dimension of x. Okay, so how do we get this? Well, we just literally so what is this? This is just dual to pi upper star. Okay, so what properties does this map have? So let me first just tell you the defining property. So what does it mean to be the dual of a map? So just the definition is as follows. So it's that if you've y in H, I guess R of y, and x in, let's see, which one does it have to be? H2 dim y minus R of x, then, well, what did we say? We say that when we apply pi star to x and cup with y, the value of our pairing, which is just trace of the cup product, has to equal, so this is the trace on x, has to equal the trace on y of x cupped with pi upper star of y. So this is just what it means to be a dual map. So it means that when you pair after using your map, that's the same as pairing after pulling back through the dual map, right? So this is literally the definition of push forward. Okay, the next property is that if y is a closed immersion, so if pi is a closed immersion, then pi star of 1 is just the class of y, so the cycle class. So this boils down to unwinding definition. Okay, 3, this follows from the functoriality of trace and the cup product. If you push forward through a composition, that's the same as composing push forwards. So 4 is a projection formula. So pushing forward a cup product of with a pullback is the same as pi star of y cup x. So this is called the projection formula. And then one more property is that then this is not totally trivial. So if pi is finite of degree d, and this is true in a bit more generality, but I'll state it in this generality. So it's true as long as if pi is proper and the relative degree and the sort of generic degree is d. So the degree of function field extensions is d. Then if you pull back and then push forward, this is just d times the identity. Okay, so how do you prove all of these things? So 1 is literally just the definition of a dual map, and then the rest of these things follow from 1. So the only one that's contentful, meaning is this 5. So here what you have to do is you have to figure out what a map of degree d does on top cohomology. So that's kind of the content. So you have to understand how it interacts with trace. Great. Are there any questions about that? Cool. All right, so let's let's go back to this. Yeah, so maybe I'll remark. I mean, so in general, so here I described what happens if if x and y are not proper. So I described what happens in the proper setting, just so I don't have to write a lot of subscripts. But in general, you get a map. Between cohomology with compact support. So you get a map pi star from HR compact support of y with coefficients in lambda to H R minus 2c compact support of x with coefficients in lambda twisted by minus c, where again, remember minus c was the relative dimension. And then also similarly, so if X is smooth but not proper, so there's some subtlety in defining this, but there's a Lefschetz formula with compactly supported cohomology. So the subtlety is that we didn't define cycle classes in this setting. So I can't actually state the theorem for you with what we've already developed. But there is such a theorem, and I'll state it. I mean, I'll state it at least in the case where phi is Frobenius later on. Okay, so maybe before proving the Lefschetz formula, let's actually just do a couple examples. So here we can actually see it's true already for some examples, given what we've already computed in Étale cohomology. So let's just consider the case where X is P1 over a separably closed field. So what are some of your favorite maps from P1 to itself?
Is X goes to X to the N?
Yeah, X goes to X to the N is great. So let's call phi X goes to X to the N. So let's compute first. So how many fixed points does phi have? So what is the intersection between the graph of phi and the diagonal? Anyone? So maybe let me assume the characteristic of K is 0, just to make things simpler. Otherwise, some kind of funky stuff can happen maybe.
Just 1?
Is it just 1?
Oh, sorry, the N minus 1th roots of unity or something? Sorry, Nth, no, N.
Yeah, any thoughts from anyone else? So we're looking at, so it's a fixed point is a point such that X equals X to the N, right? So how many of those are there?
Yeah, it's just the N minus 1th roots of unity and 0.
And 0, okay, yeah. So there's, oh, there's one more.
And infinity.
And infinity, yeah. So there's this, so it's 0, mu, n minus 1, and infinity. So okay, we found there's n plus 1 of them. So here, this makes sense. So okay, there's a little content here. You have to compute the multiplicity, but it's not so bad. So what is the multiplicity? So we have to compute. Well, we're looking at x to the n minus x equals 0, and in characteristic 0, this is a separable polynomial. It has no double roots. So we just get n plus 1 here. I mean, you also have to do the same check at infinity, but it's you just replace x with 1 over x, and then you get literally the same computation. Okay, so n plus 1 is here. So let's compare this now to the sum of -1 to the I. So we go from I equals 0 to 2 of the trace of phi on hi of p1 with coefficients in QL. So so how do we do this? So this is just there's no h1, right? So this is the trace of phi on h0 p1 QL plus the trace of phi on h2 of p1 QL. So let's compute that. So what do we get on h0? So what is, sorry, this should be phi pullback. So what do we get on h0? So what does phi do on h0 of p1? So h0 of p1 is just what?
QL?
Yeah, so it's just QL, right? And what does phi do to it? So we're looking at sections. So this is just sections to the constant QL sheaf, if you'd like. So what happens to such a section if you pull it back through phi?
Is it still just x goes to x to the n?
What is x here?
I mean, the section composed.
Yeah, so phi is acting on P1, right? It's not acting on the coefficients, right? So if if you'd like, you just have a map. Let's just think of at finite level. So if you think about z mod L to the nz, so you have a map from P1 to z mod L to the nz. So that's a constant map, right? And now what is this doing? Is you're precomposing with phi. So you send P1 to itself and then to z mod L to the n. So what happened? What map do you get to z mod L to the nz when you do that?
The same constant map.
Yeah. So here we just get the identity. Oh, I'm sorry, Arvin, I missed that you wouldn't mind a break. So once we finish this example, we'll do a break, a short break. Well, we're almost out of time, but we'll see. We'll do a short break maybe. Okay. So what about H2? So how do we do H2? Any thoughts? So how did we understand H2 of a curve? So let's just remember, so H2 P1 with, well, we're in characteristic 0, so it doesn't matter whether we do or we're over an algebraically closed field rather, so it doesn't matter whether we do z mod L to the nz or z mod L or mu L to the nz. So let's put a mu L to the n here. So this was the co-kernel of the map from pick P1 to pick P1 given by sending a line bundle to its L to the nth power. So that tells us that H2 of P1 QL, well, after you choose an isomorphism between QL and QL of 1, is just the inverse limit for n of these co-kernels. This is just multiplication by L to the n, tensored with QL, right? This is the definition of Étale cohomology with QL coefficients, or really QL of 1 coefficients. Okay, so what does phi do to this? So in order to figure this out, we have to figure out what phi does to a line bundle, right? So what does phi, what does x goes to x to the n do to a line bundle? Anyone? So what happens when you pull back the line bundle O of 1 on P1 through the map
I
x?
guess it tensors it with itself n times.
Yeah, that's right. Yeah, so it's multiplication by n. So I'll say a word about what. So this phi is just multiplication by n on pick, and hence by what the formula we wrote down, hence on H2 P1 QL. So here we get a 1 plus n, and 1 plus n is exactly this n plus 1 here. Okay. So we figured it out. Okay, so let me just briefly say a word about why this is right. So what happens, like, how do you write down a line bundle on P1? You cover by A1s, and then you write down a transition function, right, which is a function on GM, if you'd like. And so pulling back through, and then the degree of your line bundle is like the degree of that transition function, right? Yeah. So what happens here? Well, you are plugging in an x to the n into that transition function, so it multiplies the degree by n. Great.
So can you explain how, if you know that it's multiplication by n, then the trace of that is equal to n?
Sorry, you have this is a one-dimensional vector space. So a multiplication by n on a one-dimensional vector space has trace n.
I see. And the first one,
so here this is the identity, so multiplication by 1.
identity. I see. Okay, cool.
Yeah. All right, let's take a 2-minute break. Sorry, I missed your request there, Arvind. And then when we come back, we'll start proving. Lefschetz. So I'll be right back as well. All right, I'm back. I guess break over, unless, does anyone have any further questions about this example? All right, if not, let me just start with a lemma. So now we're going to start sketching the proof. So sketch proof of this Lefschetz fixed point formula. So maybe just a remark before I go on. I mean, so this Lefschetz fixed point formula is also true in topology. So it's true, for example, for manifolds. And the proof, given what we've developed, or at least what we've sketched the development of, is literally the same as in topology. So I'm gonna state a bunch of lemmas. Actually, like there's some things to check that we haven't done, like checking, for example, the compatibility of the intersection product in Chow and the cut product. And checking those things is very technical, but the proof here is absolutely modeled after the topological proof. Okay, so let's just first start with a lemma. So in order to understand what's happening here, so suppose we have phi, which is a map from X to Y. So we need to understand how to write what it does on cohomology in terms of the graph of phi. So suppose we're given an element of the cohomology of Y with say with QL coefficients, and we're gonna fix for all time an isomorphism QL with QL of 1, which also fixes one with QL of n for all n. So I'm going to ignore all the twists that show up when we do cycle classes. So those twists will go away anyway, which is why this is a safe thing to do, but I just want to not worry about it. So then the lemma is that the pullback of Y through phi, so this is a class on X, can be written as follows. It can be written as the push forward of the class of the graph of phi cupped with the pullback of Y. So here, let me say what these maps are. So here we have X times Y. The map to X is called P, and the map to Y is called Q. Okay, so what's the picture of this lemma? So the picture of this, the picture of this lemma is as follows. So here we have Y, here we have X. Sorry, maybe let me write it this way. here we have X and here we have Y. Usually you put the Y-axis vertically. And then the graph of a function looks like this. So how do we actually like realize the function? We, you know, given a point of X, you go up to the graph and then you project down to Y. Okay, so what is this saying? It's saying that if you have a class on Y, its pullback, maybe let me draw the graph in a slightly more suggestive way. So here's maybe a more suggestive graph. So it's saying that if you have a class on Y, if you want to see what happens to X, you take its pre-image, that's Q upper star of Y. Maybe let me actually use a different color. So this is Q upper star of Y here. Then you intersect with the graph. So this is the intersection. This here is class of the graph cupped with Q upper star of Y, and then you take the push forward. So here, these things are, this is the claims, this is phi star of Y. Okay, so at least pictorially, this is clear, and you could actually make this into a literal proof in topology. We can't in Étale cohomology because this class Y isn't really represented by a geometric object. But nonetheless, the statement is still true. And in fact, it follows just from the definition of push forward here. But so let me say a couple words about it. Yeah, so what I wanted to say is, I mean, this might be something a little bit confusing here, which is that this class of gamma phi doesn't live in the cohomology of X times Y. It lives in the cohomology of X times Y with coefficients and some twist, right? So what happens is, why does the twist go away? So, well, if you choose this isomorphism, it goes away, but it canonically goes away because this P lower star also has targeted in coefficients with a twist. So you in both cases, you're twisting by the dimension of Y. And so those twists cancel each other out. So that's why this makes sense as a map from cohomology with QL coefficients to itself. So this is actually like a Galois covariant map. Okay, so I'm going to leave the proof as an exercise, but I'll say a word about it. So the proof is an exercise which you should try to do. It's in Milne. You can look at Milne. But the content is just the definition. It's just the definition of P lower star, so this duality thing, plus the projection formula. So this just follows from the properties of Gaussian maps or these push forward maps that I described before. Are there any questions about this lemma? All right, so we've now, so this helps us. So this says we can write this pullback in terms of some objects that feel kind of related to like the things we've been doing with cohomology lately. So in particular, this cup product. So now we want to understand like how to write down this class of a graph here. So here's the lemma, and I think I might just have time to state it, and then I'll prove it next time. So suppose suppose EIR is a basis of HR of X with coefficients in QL. So here for each R, I have a basis, and let's let Fi 2R, 2 dimension minus R be the dual basis of H 2 dimension minus R X QL of D. Then the claim is that the cycle class inside of X times X of the graph of phi is equal to the sum of phi star EI are tensored with F2D minus R I. So here this is under the Kunis isomorphism H star X times X 2L of D with H star XQL tensored with H star XQL of D. So what is this saying? It's saying that it's saying that this choice of a basis and a dual basis actually gives us a basis of the cohomology of the product just via Kunis. So EI tensor Fi 2D minus R is a basis of this EI tensor Fj is the basis of this. And here we're writing this cycle class in terms of this basis. Okay, so this is kind of, it's almost tautological. I'll give the proof next time, but I don't think I have time to do it in the remaining 3 minutes. So let me just write proof next time. This is also doable as an exercise, and you should give it a try before next time. But yeah, so let me maybe stop there and see if there are any questions. So from this, Lefschetz is going to be almost immediate. So Lefschetz is kind of formal given what we've developed, so namely Poincaré duality and this sort of good products of cycle class maps. So I'm going to stop recording. Are there any questions?